Hi. In this video, we're going to be talking about section 13.3. This is the second video. We're going to talk about curvature. So the general idea of curvature is that some curves bend more quickly than others, right? So if we have this kind of spiral here, we would notice that, well, some parts are more curvy than others. I mean, this is not a revolutionary idea. What's going to maybe look confusing at first is how we're going to define what that curvature is. Like, how should we define curvature? How should we define curviness of this spiral? So we're going to do a few things, like let r of t, okay, be a vector function, have arc length given by s, okay, s of t. So like s is measuring the arc length of the function at any point. Like we're saying, starting from here, as c equals 0, we're going to measure how much length have we accumulated on this function, okay? S is not a vector. S is not a vector. I'm not making a mistake here. It's important that S is just going to be a measurement of the length, okay? We want to recall that T of t is the unit tangent vector. And so it's like the formula we had was something like this. It's the derivative of r divided by the length of that derivative. Okay. And that unit tangent vector is sort of telling us the heading of the curve at any point, right? Where we're making it a unit vector, so we can just think of this as giving us a direction. So we're going to define curvature as a letter kappa. So it's a Greek letter K. You probably can just write K and no one will notice. We're going to call it the length of the change in t, the change in the unit vector, divided by the change in the length. So I guess my job right now is to convince you that this makes sense. Well, so if we're changing our length and we're keeping that constant, like we have one foot more and we have a big change in the heading or the direction we're moving in, that would result in a big curvature, right? So again, think of this as like changes in slope over a change in foot of the function. So over here, you know, my heading is there, and then here my heading is maybe a little bit higher than that, something like that. Over that same length, the vector, the tangent vector, didn't change that much. But when we get to here, if I want to keep that length constant, it'd be like this guy is going that way, and that is going straight up. Can't draw it too well, but picture it going straight up there. So over that same length, the direction I went changed a giant amount, right? So higher kappa value, a higher curvature means more curvy, okay? Make your own jokes here. So we're going to talk about this guy being curvy by saying that, well, when I try to trace a length, my direction changes a lot. A big change in direction over the same change in length is what we're going to call curvature. All right. Now, ideally, we want to have a nicer formula for this. So notice that a change in length over a change in time, right? That s of t is supposed to be the integral of the derivative, the length of the derivative of r. So ds dt equals, well, we would get rid of the derivative. Well, sorry, the derivative would get rid of the integral, so to speak. It's just going to be the length of r of t. Right? That is literally a consequence of the formula that we had in last section for how we're getting arc length, right? If the arc length function would be the antiderivative of the magnitude of r prime blah, then ds dt would be this. So another formula for kappa, another formula for curvature, it's going to be the derivative of the tangent vector, the unit tangent vector, divided by the magnitude of r prime. Oops. I'm going to center that so it looks a little nicer. Or we could just write this like it's excessive to have two magnitudes. It's the magnitude of t prime divided by the magnitude of r prime. And that's a much more nice formula. All right, so in summary, we're going to have the following formula for curvature. Formulas for curvature. I'll point out one more time. This is kappa. Kappa is going to be a scalar. It's going to be a function of time. We'd have to define the curvature of a specific point on our function, but it's a scalar, it's not a vector. The formula we just gave will be useful sometimes. So the magnitude of the derivative of the unit tangent vector divided by the magnitude of the derivative of the vector function itself. The book has a proof of what I'm about to show you, but basically, through a lot of work with the cross product, you can get this formula. You're going to take the magnitude of the cross product of r prime of t cross r double prime of t, the second derivative, and divide all that by the magnitude of r prime of t cubed. This is not a nice formula. It's not something I'm going to expect you to memorize in this class. This formula would be given to you. But as always, I expect you to know how to use either of these formulas. You certainly do not have to prove it. If you want to look at the proof in the book, feel free. But I don't know if it's particularly enlightening, okay? So we're trying to compare how is this first derivative working with the second derivative. The cross product is going to give you a vector that's perpendicular to both of them, and that would be the derivative of the unit tangent vector. Okay. Again, it's the first formula over here that I want you to focus on. That formula, however hard it is to understand, will make more sense over time. It's how much is our heading changing, the direction we're going in, how much is that changing? Change in direction over the change in length. That should make sense. Especially if you start thinking about keeping that change in length fixed. The most important thing I can give you, most important hint, if given a specific time, t equals a, plug that in plug in A after your derivatives, obviously. It's going back to Calc 1, but before cross product and length. I hope that's really clear to you, because that's where really a lot of things can go off the rails. These formulas are obviously going to be really complex. Cross product is a pretty complicated thing to do. Length has a lot of square roots and squaring in it. You want to deal with numbers as much as possible when you're trying to do something as complicated as curvature. That's my main bit of advice for you. So we're going to start off with something simple. Find the curvature of a circle with radius 4. Okay? So they ask you that. Your first goal would be to get a vector function that gives you that circle. And we're going back to parametric equations. That vector function would be something like this. R of t, notice it's a vector function, 4 cosine t in the I component plus 4 sine t in the j component. You could even think of it as a plane curve with a 0 in the k component, but I'm not going to do that right now. We're just dealing with a nice simple function. So you can do r prime pretty easily. It's going to be negative 4 sine plus 4 cosine t. And to check your understanding from the last video, we're not asked to find the curvature at a specific point. For a circle, it's always going to be the same. It's always turning the same amount. But to check your understanding, can you right now find out what the magnitude of that vector is, of that r prime vector? Pause the video if you don't want to see me go further. So it should be negative 4 sine t squared plus positive 4 cosine t squared. You should have gotten 4. It's going to be 16 sine squared t plus 16 cosine squared t, which is an example I think we did in the last video, or close to it, which is just 16, which is just 4. The square root of 16, which is just 4. Okay. Why do I need that? Because now I can say, all right, t is r prime divided by the length of r prime. And for a circle, at least this formula is pretty nice. 1/4 for the dividing by the length times our beautiful little r prime function, which is going to cancel out those coefficients. And that formula says we're supposed to take the derivative of that. So I'm definitely getting tired of this too. Don't worry if you're saying to yourself, well, this just seems like a big slug. It definitely can be. No ifs, ands, or buts about that. We need to figure out the length of this vector now. So go ahead and give that a try. Go ahead and give that a try. 3, 2, 1. So we're talking about cosine squared t plus sine squared t, and that's just 1. So the curvature at any x value, at any t value, at any t value, in case you lost the thread about why are we doing this, it's the magnitude of the change in the tangent vector divided by the magnitude of the change in the length, or the change in the r. And so what we're talking about here is 1 over 4, or 1/4. So the circle is a good example of a function that has constant curvature, right? So when we draw a circle, we can see it has a pretty constant curvature. It's always changing, it's always turning. A perfect circle, one that I can't draw, is always going to turn the same amount every single time. It has a constant curvature. Okay, circles in some sense are an idea of what it means for a function to have constant positive curvature. Okay, zero curvature would be a perfect line. And really high curvature, you could think of it as being a really small circle, right? The smaller the circle gets, the more we have to turn per length along the rim of the circle, along the circumference of the circle. Okay? So, let's do another one. Now we're dealing with a real function. Let's look at the twisted cubic again. T squared, t cubed. Use kappa equals r prime cross r double prime divided by r prime cubed. Okay. To find curvature when t equals 0. Okay. So, what do we want to do? Usually how I end up approaching this is I'm going to write down, if I'm using this formula with all these derivatives in it, I want to find r prime and I want to find r double prime. Okay. Please go ahead and do that. 3, 2, 1. 1, 2t, 3t squared. And that, of course, means r double prime is 0, 2, 6t. So, what's next? Because I have a specific time value, now is when I want to plug things in. So r prime of 0 is 1, 0, 0. R double prime of 0 is 0, 2, 0, right? That is going to be a lot easier to do a cross product of than this. And we're going to do both. I'm just going to show you what it looks like when you're doing it to find a specific curvature versus the curvature formula. So, to find the specific curvature, the kappa at 0 is supposed to involve, let's do the cross product of 1, 0, 0 with 0, 2, 0. And please do not think yourself a genius. Okay? Most people can't do cross products in their head. I'd rather see you write it out and get it correct than see you do it in your head and get it wrong. I mean, I've seen plenty of people write it on the paper and still get it wrong because you're not that familiar with cross products as you want. Try this cross product out right now. See if you get the right answer. 3, 2, 1. I'm talking about 0i minus 0j plus 2k. So the magnitude of r prime of 0 cross r double prime of 0, that's what we just found. This is r prime of 0 cross r double prime of 0. Sorry if that wasn't clear. So the magnitude is just going to be 2. When you have a vector and its only length is in one direction, the magnitude is just going to be 2. the magnitude of r prime of 0 in the same way is just going to be 1. So the curvature at 0 is just 2. Okay, which is pretty curvy, right? Our curvature being 2, it means it's, the same curvature as a circle with a radius of 1/2, right? Like a really tiny circle. It's that kind of curviness. That's what we're thinking. Because you saw that for a circle with a bigger radius, it's 1/4. That relationship is always going to hold. The bigger the radius, the less the curvature. So we're thinking tiny radius, really tight turning. This is a function that came up and wrapped itself around like that. And it's that kind of curvature right there that's getting really tight and twisted. It's a twisted cubic. Okay. Find the curvature formula for r of t equals t squared t cubed. Okay, so this is where it gets a little harder. And this is why, again, I'm trying to show you, if you have a t value, plug it in. But we just did this in the last slide, so forgive me if this is going too fast. But I'm just basically copying down what we just did. So now I'm meant to get r prime t cross r double prime of t. And here's what I'm trying to tell you when I'm talking about why you would want to plug things in first. Because this situation is pretty complicated just to look at. And we can see how well you do when you're doing this cross product if you try it out. Please try it out now. 3, 2, 1. I'm getting 12t squared minus 6t squared in the I direction. Subtract the j direction always. 6t in that j direction plus 2 minus 0 in the k direction. I guess I could have written 6t minus 0 in the j also. Sorry. So that's 6t squared I hat minus 6t j hat plus 2k hat. And then you need to find the length of that. And the goal of this is not to bother you guys with how difficult this can be. It's mostly just to keep track of all this stuff and see how you can do with it. Okay. This is really important for certain areas of differential geometry is what the subject's called, which is really important in developing spaceflight. And nowadays all the computers do this stuff, but someone has to program the computers, and it's people who take classes like this. So what's the magnitude of that? We're going to do 6t squared. That's 36t to the 4th. Minus 6t squared would be 36t squared plus 4, which does not simplify nicely, much to our chagrin. And we're going to have to divide that by r prime of t, of course cubed, but first we have to find r prime of t. 1 plus 4t squared plus 9t to the 4th. I'm just taking these values, everybody. That's how I got that. So the curvature formula, and it is a scalar, I almost said squalar, 36t to the 4th plus 36t squared plus 4 divided by this square root, 1 plus 4t squared plus 9t to the 4th cubed. A lot of the times you'll see that bottom number recorded as a fraction power. Oops. What am I saying? I'm saying a lot of times you'll see it like this. One plus 4t squared plus 9t to the 4th to the 3/2. Nothing's making that nicer, right? But the point is, now that we have that formula, we could plug in any value. But you can see why I'm telling you, for exam purposes or homework purposes, plugging in things first makes this go a lot easier. Special case to end on. Let's call it functions. Like classic 2D functions. Like y equals f of x. All functions are plane curves. So we can parameterize like y equals f of x can become r of t as a vector. We're going to make x equals t, and if x equals t, then the y is f of t, and what would be the z component? It would just be 0, right? And that's the kind of stuff we could do to make short work of all 2D functions. The book will actually give you a formula to use for functions. I'm trying not to overwhelm you with these formulas. I'd rather you just understand, hey, well, I could do this parameterization. And you know, we can give you functions like x equals some function of y. What would that look like? That would look like r of t. You would make y the parameter, x is that output, and then still z equals 0. Right? And for a lot of other, 3D curves, you could do similar parameterizations, right? Like if you had the parametric equations, it would just be the first two components, and the last one was zeros. So that's what you would want to do for plane curves. I'm not going to give you too many examples of this. Let's just do one together. The book has another one if you want to see that, but it's going to use the formula. The book wants... So let's say we had find the curvature of y equals x cubed plus 1. Okay? So what you would do is parameterize it as a vector function. So I'm just saying, like, instead of using x as the input, let's use t, and that would make the output t cubed plus 1. And because we're thinking of this as a function in the xy plane, the z coordinate's always going to be 0. Maybe I didn't say that earlier. I hope that makes sense. And then the steps are the same. You're going to find me r prime, r double prime. You're going to want to do the cross product once you find that. The magnitude of that cross product. It's a good chance to check if you understood everything we've done in this video. And the magnitude of r prime of t itself. Pause the video right now and try it out. Here I go. 3, 2, 1. Easy peasy. 3t squared, 0, 0, 6t, and 0. That's all it is. It gets a little easier with plane curves, right? Because one of these is only changing very linearly. So derivative, second derivative is going to have a lot of 0 in it. and therefore my cross product is going to be just 6t in the k hat direction. Check your work and see if you got that. And so the magnitude is just going to be, I'll show the work here, 6t squared, which is going to be 6t. Technically, it's the absolute value of 6t. We're just going to let it ride. We're not going to worry about it too much. What's the magnitude of just r? It should be 1 plus 9t to the fourth. And so the curvature formula that you're supposed to be assembling here is supposed to be the magnitude of r prime cross r double prime all over the magnitude of r prime cubed. So 6t, sorry, I can't help myself. That's got to be the absolute value. All over 1 plus 9t to the fourth, all to the 3 halves. To make sure you're accounting for the square root as well. Okay. Work on your cross product skills, try out a few of the examples on the homework, and come back in the next one where we'll go over the final parts of 13.3. See you in that one. Bye.